Very smooth. Excellent job, us. Today we're really excited to have Maya Fishbach here. Maya was a graduate student at University of Chicago, and then was an Einstein Fellow at Northwestern, and starting this year is a professor at CETA. She's going to talk to us about black holes and astrophysics.
Yeah, thanks so much for having me here. And today I'll tell you about a few of the things we've learned from LIGO-Virgo-KAGRA's black holes. And this is work done with a bunch of collaborators over here, including the 1,500 plus authors in the LBK. Okay, so the black holes I'll be talking about today are in these binary systems. So we have this gravitationally bound pair of black holes, and they're inspiraling towards each other and losing energy and angular momentum through this gravitational radiation that then propagates out and travels for billions of light years across the universe until it reaches us here on Earth. And we're able to detect it routinely since the first detection in 2015 with these gravitational wave observatories that consists of these two LIGO detectors in the US, Virgo in Italy, and then KAGRA, which has recently come online in Japan, and LIGO India, which was just officially approved by the Indian government a few weeks ago, and will hopefully come online later this decade. And so this is an especially exciting time to be talking about gravitational waves with these interferometers because, or depending on how you look at it, if it's exciting or not, but this here shows the time and when we've been observing. So there was this first observing run that resulted in a few detections in 2015. And then we had the second observing run that brought the number of detections up to 11. And then we had this third observing run where we have around 70 to 90 events. And then we've had this very long break here where we were not observing. Part of that was COVID, and part of that was supply chain delays, et cetera, et cetera. But now we are right here. So the detectors are going to turn online again tomorrow for an engineering run. And then the fourth observing run will finally start at the end of May.
Well, when you say the detectors turn around on tomorrow, if a big event happens on Friday, which has been the pattern, will you be able to use it?
Technically, no.
But
yeah, but we don't have everything fully ready so that we'd be able to like communicate it in the appropriate channels. So it'll just be for testing. But if our one binary neutron star happens during the engineering run, then I don't know. I think we're gonna try to salvage it.
Seems like a good idea.
So it starts up with a set of engineering tests that lead to the thing, or is it really like locking the system? Is it more like?
Yeah, so the system, it's been locked on and off throughout, especially the past few months. So there have been like gravitational waves that have gone by, and like some of them we've actually found like, oh, it's good to know black holes are still emerging out there. But yeah, it'll be really just trying to prepare everything, so like running the detection pipelines, but not everyone has to be ready tomorrow. So it's just a series of like mostly testing the analyses, like the detectors are good. Yeah, and so every time we turn back on, we're a little more sensitive than the previous run. So by the end of the next observing run, we should be up to a few hundred binary black holes and hopefully a few binary neutron stars. Big Poisson error bars on that. Yeah, so this plot is one way to visualize the events that we've seen so far with gravitational waves. So again, each event is this pair of black holes that merges together to form a bigger black hole. That's what you see in the blue. The y-axis here denotes the masses of all of those component black holes. And then in orange here are events that contain neutron stars. So these represent neutron stars, which we can pretty much identify as neutron stars in our data just because they're below around 2 and a bit solar masses. So like some of these events we're not sure about.
The KAGRA wasn't part of that, right?
No, KAGRA is not very sensitive. So their data hasn't actually been used for any of this. They also weren't on until like the last week of the most recent observing run. So the instrument has not contributed to these detections, but we're kind of one like mega collaboration now.
How are these? Every time I see this plot, I always wonder how are they ordered?
Oh, yes.
Because it looks like it's like final mass from the center outwards, but then there's some weird
It's
cases.
just to look cool.
It's
Yeah.
designed to look cool.
Yeah, I don't know, it's like a
So-
butterfly or airplane or something. But you can, there's like a web interface that Aaron
I see.
Miller made, and you can
Oh,
order
you can
them how
reorder
you
them
like.
as you like. Okay.
Yeah.
So what are these again? The arrows point, so they're merging
Yeah, so
dependent, or-
each arrow is like one gravitational wave event. So there are 2 black holes that merge and form this black hole. So like this is the merger, and then there's this final black hole that sticks around. So there are like 90 arrows on this plot that represent all of the events. So 90 compact binary coalescences observed to date, and that's published in GWTC3, which stands for Gravitational Wave Transient Catalog 3. So that's all the data we have right now, and there's actually a lot that we have already learned about these systems. So some of the questions that we're trying to answer is, first of all, like how are black holes in the universe made? So these are stellar mass black holes that we're talking about, meaning they have masses between a few and 100 times the mass of the sun. And we know that one way that our universe makes such black holes is through stellar evolution. So this is a diagram that's kind of old at this point, from 20 years ago, but the basic idea is that depending on the initial metallicity and the initial mass of your star, so talking about massive stars that are around 10 times more massive than our sun, at those relatively low masses, you end up with a neutron star, and then at low enough metallicities and high enough initial masses, you end up with a black hole. And exactly how that black hole is made, we're still not really sure about, whether it's a supernova that then has some fallback material onto the core and makes this black hole, or whether you just get this direct collapse of the stellar core without any kind of explosion. And then there's also this area here that's whited out, where we think that at very low metallicities, for pretty massive stars in this mass range, you don't end up with any black hole or neutron star at all. The whole star just destroys itself in this parent stability supernova, and I'll come back to that a bit later.
How should I think of where these divisions came from? Like these are the result of, like, what calculation leads to these lines?
So it's a lot of simple assumptions about, there are these mass limits, right, to where you can go, like from helium burning, like when you can continue past helium burning, for example, and then when you can continue past carbon burning, and that happens for like specific temperature ranges, so that depends on your initial masses. But these lines about like distinguishing the type of supernova explosion, I think that is like unknown.
Right, but like at high mass, like this metallicity dependence that's based on some, is that like coming from winds, assumptions about winds or something like that?
Yeah,
Okay.
yeah, like how much mass loss you have. But a huge caveat here too is that this is based on single stellar evolution. And so this
Right.
can get a lot more complicated in binaries because you lose mass not just through winds. And it can also get more complicated because I think, well, I'm not sure about this paper from 2003, but a lot of these things that you see are also based on extrapolations of the low mass stars. And so very massive stars actually do pretty different things, like they lose their hydrogen envelopes while they're still in the main sequence and go through like they're essentially a Wolf-Rayet phase if they don't expand into red supergiants. And so there's like some complicated stuff here that is simplified, which I think is partially where the sharp line comes from. Is simple.
Okay.
What were you gonna say?
Oh, I was just gonna say,
Yeah.
this is a grid of stellar evolution models run with Kepler. What Hager did is he just did a bunch of different masses and ran them and got different results. And these lines were just based on different shell burnings that happened in those models.
Yeah, I did mean to update this plot because Hager and a couple of other people have like a review that just came out last week that is on forming black holes through stellar evolution. But they didn't have this plot. They had like other plots in it, but I don't know. They didn't have like the metallicity dependent.
And these just standard stellar evolution models predict whether or not you collapse to a black hole.
Yep.
Okay.
Okay, yeah, so in order to have gravitational wave sources, we actually need to have two black holes that merge. So then another question that we want to understand is how are these merging black holes made? And so there are kind of these two classes of formation scenarios that people talk about that are split into isolated versus dynamical. In the isolated case, you start off with two stars, sometimes more, that live their life in a binary, and then one of them explodes, turns into a black hole, the other one explodes, turns into a black hole, and then for some right conditions, a very small fraction of the time, you can have it so that those two black holes are close enough together that they can merge within the age of the universe and emit gravitational waves that we can observe. And this is kind of a challenge because you need these two black holes to be close enough together, but if you start those two stars that closely together, then as the stars expand, one of them will just swallow the other one. So you kind of have to have very special conditions in order to make this work. The other kind of formation channel, which is again a class of these formation channels, is when you have a dense stellar environment, then you can end up with a bunch of stars that turn into a bunch of black holes that are dynamically interacting with each other, and they can dynamically assemble binaries that again merge within the age of the universe. And this can occur in a variety of different environments, like globular clusters, we'll talk about a bit later, as well as AGN disks around supermassive black holes. Oh yeah.
Do you know the fraction of, because it sounds like the dynamical one is much easier to do, or the majority of events that you observe that, or is that something that you're still trying to understand?
That's something we're still trying to understand. I will share some results on that. I mean, most massive stars live in binaries in the field. So in some sense, it is, if you start off with a dense environment, it's sometimes easier to make the dynamical channel work, but it's not, you still need it to be pretty dense because you need it to have a high enough escape speed that like when these black holes are formed, they're not going to get kicked out from supernova a lot of these, the kind of capture events can also, and the gravitational wave emission itself emits anisotropic waves that can also pick objects out of the clusters. So it's not obvious that there are a lot of such dense environments in our universe that this would work for. Yeah, and then kind of looking at the bigger picture, we're also trying to answer where and when do black holes merge. So how does this tie into large-scale structure? For example, what are the host galaxies of these gravitational wave events? Can we learn something about large-scale structure just from gravitational waves alone, as well as the cosmic expansion history? So we can actually measure cosmological parameters with gravitational waves, which I won't talk about at all in this talk, but I also work on that, so feel free to ask me some other time. Okay, so for the rest of the talk, I'm just going to tell you a bit about these 3 questions, again, related to how, where, and when these binary black holes are made. And so the first thing I wanted to talk about was hierarchical mergers, and then I'll talk a bit about delay times, and then a bit about the host environments, particularly globular clusters. In order to answer these questions, we have to start from the gravitational wave observables. So with gravitational waves, we can measure how big each black hole is, how fast they're spinning and where the spin axis is pointing. And then we can also measure the luminosity distance to the mergers, which, assuming a cosmological model, tells us a redshift and like how old was the universe when this merger happened. So all of these things together tell us how, when, and where our black hole is made if we can interpret this gravitational wave data. And so to do this, the statistical techniques that I employ is this hierarchical Bayesian inference. And so we're fitting a population model to these single events. This population model describes the distributions of the masses, spin, and redshift. So for example, we can fit a power law to the black hole primary masses. So the power law might look something like this. And as a first step, we measure the masses of all of those black holes. That was in that fun plot that I showed in the stellar graveyard. But then we can fit these higher level parameters like the minimum mass, the slope of the power law, and the maximum mass. And when I'm presenting these population distributions, these are the underlying population. So the measurement uncertainty and selection effects are undone. And so what I mean by selection effects, this is one example, and the main selection effect we have to deal with, which is that big black holes are overrepresented among our gravitational wave events because the bigger black holes emit louder gravitational waves. So if we look at the volume to which we are sensitive to source with a given total mass here on the x-axis, then that grows roughly as a power law. These bigger black holes, as we get closer to 200 solar masses in total mass, they're emitting louder gravitational waves. We can detect those out to larger distances, and therefore we're probing a larger volume. So they're overrepresented in our catalog, but when we fit things like this power law distribution, we take that into account, and so this is the underlying distribution of things that merge out there in the universe, even though these ones are more likely to be detected.
It saturate. Why does it saturate?
Oh, here?
Yeah.
Yeah, because these start to merge at lower frequencies, and so they go out of band.
Okay.
Yeah. Especially as they get redshifted.
Right.
But those would be detectable with LISA?
So LISA doesn't, so we're missing a frequency bin. So the ground-based, with ground-based, it's really hard to get below 10 hertz. Maybe the next generation of proposed detectors by like going underground and kind of reducing or improving the seismic isolation can go to 5 hertz. But LISA is we're kind of missing this decihertz regime. LISA is like millihertz. And so in the few hundred solar mass range, we don't have a detector that's like great for those right now. LISA sensitivity really starts at like 10 to the 4th solar masses. Yeah, few hundreds is hard. There are proposals like build a LIGO on the moon and other ones, like LISA with smaller arms. Okay, what am I doing on time? Great. So yeah, the first astrophysical lesson that we can get from these events that I want to talk about was hierarchical mergers. So the question here is, do black holes grow through repeated mergers? Which is very simple. We know that black holes can form from stars. That was that plot from paper in 2003 that I showed before. And so the gravitational wave events that we might be detecting are, okay, you had two stars that gave rise to these two black holes, and then those two black holes merged. And I'm going to call black holes that form from stars first generation or 1G black holes. So we might be observing mergers from these first generation black holes, but when those first generation black holes merge, they form this second generation or 2G black hole. So we might also be observing mergers from these 2G black holes, like a 2G plus 2G black hole, or a 2G black hole that merges with another 1G black hole. So are the black holes that we're observing that are participating in these mergers formed directly from stars, or are they formed from smaller black holes? And one reason we care about this is because we know that it can occur if you have a dense enough environment. So this is from a review that Davide Gerosa and I recently wrote, and you can see that there are a lot of environments that can give rise to these first generation mergers, but then some of these densest dynamical environments, especially things like EGN disks or nuclear star clusters, and maybe the densest globular clusters, are dense enough so that when those two black holes merge, their remnant can stay in that dense environment and then find another partner and merge again. So this is just something that would happen if you have a dense enough environment. Another reason that we really care about this after the most recent observing run is that we've observed some really massive black holes. So this plot shows the merger rate as a function of black hole mass, similar to that power law cartoon I showed before, but this is actually what we've measured. And so the latest measurement is this blue one that's shaded, GWTC3.
And we should think of this as you've dealt with the selection effects.
Yes. Okay. Yes. So we've assumed some model, it's a power law plus this Gaussian peak because we've observed this excess of black holes over here. And the thing to take away right now is that we've observed some black holes, the rate is non-zero all the way up to 65 at least. So probably all the way up to 80, the rate is non-zero. We have black holes that are participating in mergers up to around 80 solar masses. In particular, 1% of mergers involve black holes heavier than 40 solar masses. And the reason that this is important and was kind of surprising at first is because of this theory of parent stability supernovae. So if black holes are formed from stellar collapse, we expect them to experience, if they're in this certain mass range, apparent stability in the stellar core, which would lead to an absence of black holes between around 40 to 60 and around 120 to 130 solar masses on the other side. So this is, again, just a cartoon, but the idea is that we would expect that stellar collapse leads to this gap in the mass distribution where we don't have any black holes formed from stars. But we have seen black holes at least up to here in our data. And so maybe those black holes are not formed from stars, but they're formed from smaller black holes instead. And so what I'm going to do in the next few slides is show some results where I'm using spin to distinguish hierarchical mergers. So one way, in addition to those hierarchical mergers being more massive, bigger black holes, they also have a distinct signature in their spins. So there are two things here. One is that those second generation black holes tend to spin at a dimensionless spin magnitude of around 0.7. And the second thing is that hierarchical mergers are assembled in these dynamical environments. And so we expect their spin tilts to be randomly oriented. So relative to the orbital angular momentum, there's no preference for alignment or misalignment. They're just random.
So you're assuming, there's hierarchical mergers that could occur because like there's like a quadruple system or something that's hierarchical, like a hierarchical, just stellar system, right? Is that what you're talking about? Or are you talking?
No.
No.
Yeah, that's actually pretty hard to do, just because gravitational waves are so inefficient at shrinking orbits. It would be really hard to get there to be. I mean, I guess if you have a quadruple system where you somehow have to drive
It's
the
just
inner
like
ones to merge.
When is it that when they're stable that this time scale is going to be too long?
Yeah, you would need to drive some like
You need
know,
something
linear
else going on.
oscillations. Yeah, like so you really need to have like a very dense environment where you're frequently exchanging binaries and having that dynamical capture in order to get the separations small enough.
Okay. So okay, great. Thanks.
Yeah.
Are you gonna explain these more, or
You
like
can
the first comment I'm puzzled by?
Oh, the first one?
Yeah.
I can explain that. So this is in the limit where the two black holes are relatively similar in mass, which is kind of what we expect to happen. So if they're closer to each other in mass than like a 2-to-1 mass ratio, then the main source of angular momentum in that binary is the orbital angular momentum. Like the initial spins of the black holes are kind of irrelevant compared to the orbital angular momentum. And then the orbital angular momentum at the point of merger, like at that last stable orbit, it just corresponds to this dimensionless spin of 0.7. So that's how much you just get from that orbital angular momentum. Then you form this bigger black hole, and its angular momentum is coming from that orbital angular momentum at ISCO, and leads to this 0.7.
Independent of what the things were that were doing the merging, whether they were stars or two black holes or anything.
So if they were two black holes, this is in the two black hole case because it's the angular momentum at that innermost stable circular orbit.
Right, but wouldn't that be similar, independent of what was merging, or not?
I think if you have two stars, then they're merging. Then I think you could throw that off. Also, the stars can have a dimensionless spin parameter that's much larger than black holes.
Oh, okay, because they're so big.
Yeah, so 0.7 is really like when you have two non-spinning black holes that are equal mass, and then by adding spin to those black holes, or by changing the mass ratio, you can change that around a little bit. But yeah. Okay, so these two things, basically, if we could measure the spins of these two black holes, these dimensionless spins, chi1 and chi2, and their spin tilts, then we can use these traps and distinguish hierarchical mergers just from the ones that have these two properties. That's really hard to do because measuring individual spins with gravitational waves is pretty tough. So instead, you can get a much better measurement of this one parameter instead of 6 parameters. We divided it into one and get this effective in-spiral spin high effective. And that is just this mass-weighted average of the two spin components projected onto the orbital angular momentum axis. So it's given by this expression here, but basically you just take the component of each black hole spin that's projected along L here, and then take the mass-weighted average of those two things. And so we're going to look at high effective for every event, and then look at the distribution. So this is the cumulative distribution function that you'd expect from hierarchical mergers for high effective. Both the 2G plus 2G and the 1G plus 2G case is overplotted here. And there are two characteristics. One is if you look at the center of the chi-effective distribution, so where the CDF is 0.5, that is at 0, and that's just the random spin orientation. So half the time you get spins that are aligned with the orbital angular momentum, and half the time they're misaligned. So we expect chi-effective to be symmetric around 0. And then the other thing is just the width of this distribution. So it extends to fairly large, at least bigger than 0.3 and smaller than negative 0.3 on either side. And that's just because we have black holes with spin. They're spinning at around 0.7. Chi-effective is going to extend to fairly positive and negative values. So that's what we expect from hierarchical mergers. Now we can look
Marcus had a question.
what we've actually observed. Oh yeah.
So we can't know chi1 and chi2. How do we calculate chi-effective?
Oh, so chi-effective is something we get from the gravitational wave signal. So it basically affects the frequency evolution of the gravitational waves to first order. So we just get this parameter instead of measuring chi1 and chi2 that well. Oh yeah, but before I get to observations, there's one fact about this that I will highlight, which is that in particular, there's this robust prediction that 16% of hierarchical mergers, or 16% of gravitational wave sources that involve a hierarchical merger product will have chi-effective less than negative 0.3, regardless of whether it's 2G plus 2G or 1G plus 2G. And this simple fact allows you to, if you could measure the fraction of sources in the population that have chi-effective less than negative 0.3, you can very easily get an upper limit on the fraction of sources that involve a hierarchical merger product. You just take that fraction and divide it by that 16%. So that's what I will do. If you look at what we've observed for the population distribution of chi-effective, so this is that, again, that CDF, cumulative distribution function for chi-effective, and these are the observations for two different models. The details don't really matter, but the mixture model gives you a more conservative upper limit. Basically, we have not observed a single source with chi-effective less than negative 0.3. These models just allow you to put an upper limit on what's the underlying fraction in your population, which is at most 3%. So you can take that 3% and divide that by that 16%, and you get roughly 20%. So it implies that less than 20% of binaries involve a hierarchical merger product.
That's to say, of the binary coalescences seen by LIGO-Virgo.
Yes, although we have taken into account selection effects, but basically of the type of binary black hole mergers that we could detect.
That contributed to the observations.
Yeah.
So that's somehow weighted over all the different masses and.
Yeah, so that's what I'll show here, which you can look at this. Yeah, this was just taking all of the events together, assuming they have the same they come from the same chi-effective distribution regardless of their masses.
It's really puzzling in a way that you can get such a strong limit, it seems like.
Yeah.
That not seeing the exceptional small ones, the small chi's, can somehow, and I guess you're just saying that if they've merged hierarchically and they were black holes, that's what you mean by hierarchical mergers that started from black holes.
Right, yeah. So when you have
Then there's gotta be more that have a high spin than we're seeing.
Yeah, so we basically, this limit just comes from the fact that we've seen around 70 events and few of them have had, like we can actually say that none of our events have chi-effective less than -0.3. Like none of, even within uncertainties for individual events, they just don't extend that negative. So it's like 1 out of 70, corrected for selection effect. Okay, it's actually harder to see those negative chi-effective systems. And so that leads to this 3%.
And it must be critical that the incoming spins are randomly oriented, right?
Yes.
Like, so you could evade this by some special orientation of spins somehow. I don't know how you would do that, but
yeah. So in an AGN disk, you can do that. I'm not going to talk about it. I think it's still hard to get it to always be prograde, like aligned with the AGN rather than retrograde, but you can definitely avoid having like insane spins, for example.
okay.
Yeah. But yeah, I'm really pumped about that. Yeah, the last thing I wanted to say about this is, okay, you probably expect that if there are hierarchical mergers, like these 10 or 20 solar mass black holes are less likely to be coming from hierarchical mergers. Like they're probably going to make bigger black holes, and so we expect them to be more common at higher masses. And so you can fit this chi-effective distribution and allow it to vary with mass. And so that's what I did here. And then this plot just summarizes the fraction that I measured of chi-effective less than -0.3 as a function of that primary black hole mass. And then this axis here is converting this fraction to the hierarchical merger fraction. And the first takeaway is that there's no, even though it looks like everything goes up as we go to higher masses, there's no evidence in the data that happens. Like the data is perfectly consistent with this being 0 across all masses. But the data does permit for these more massive systems for chi-effective less than -0.3 to be more common at these higher masses, and therefore hierarchical mergers to be more common among these higher masses. But it's pretty interesting that the hierarchical merger fraction can't be 1, can't explain all the black holes until you get to around 60 solar masses. So even if we're talking about 50 solar masses, some of those, if the alternative to hierarchical mergers is being directly born from stars, some of those 50 solar mass black holes probably come from stars. They're probably not all made from smaller black holes. So this suggests that stellar evolution can make black holes up to 60 solar masses with some caveats.
And that limit is, I should think of it as how many sigma? Like what's the
yeah, this is the 95%
Got it.
upper bound. Yeah. Okay, and this is the summary to this first part of the talk. I'm not going to get to all 3 parts, but I'll pause here and see if there are any other questions about this.
But from the gravitational waves for the most massive LIGO black holes, there's no evidence for spins of the progenitors, or they're consistent with 0, or?
Yeah, they're consistent with 0. They are consistent with 0.7. So one of the caveats to this conclusion here is that there is some model here. We don't have enough events to really like bin up the space finally and look at, okay, like events in this mass bin and this mass bin and this mass bin. So I'm assuming that the chi-effective distribution varies kind of gradually with mass. So if you said, okay, everything up to 50 solar masses comes from one channel, I can explain those, spins are 0, but then there's this other channel that produces only the massive black holes and that has large spins. Like, you could make this, if you put like a step function here, you could make that fit the data, but the motivation for having something that's more gradual is if you're forming 80 solar mass black holes from hierarchical mergers, like probably from 240 solar mass black holes, some of those 40 solar mass black holes are then in those environments. So you should, in my view, you should have kind of a smooth transition here if you're having those environments contributing to the rate. Okay, let me move on then. I'll skip this. So the other two things I wanted to talk about was delay time and host environments. I think we're just going to smush these together in 10 minutes. But both of these things kind of rely on this measurement, which is, before I showed some mass distributions that we measured and some spin distributions that we measured. The last property that black holes have is their merger redshift. And so this is showing the merger rate as a function of redshift that we've measured with the latest catalog. And in this dashed black line here, for reference, shows the star formation rate. So we can get this merger rate from around redshift 0 to around redshift 1, which is kind of the furthest redshift that we've observed any mergers. And we expect that the star formation rate like peaks up here at redshift 2 and then decreases. And our merger rate that we measure follows the progenitor formation rate and some delay time distribution. So basically here, time is now moving in this direction. But right, we start with the birth of the universe, and then you have stars that are born at some redshift, and then very shortly after, because these are massive stars, so they live fast and die young, you have the black holes that result from them, so that's a pretty short delay. But then there can be this very long delay from the gravitational wave in spiral, because gravitational waves are just so slow at shrinking the orbit. And then there's the merger, and we observe the gravitational wave here. So even though we observe gravitational waves at some merger redshift, the stars that they originally came from may have come from much higher redshift at much earlier times. And this delay that we have here is really telling us a lot about the physics by which those black holes merged. So an example of that I showed, it is just this collection of figures here, which shows different formation channels. They predict different delay time distributions. The black holes will take longer or shorter to merge. And one in particular that I'll call out is this chemically homogeneous evolution, which just involves two stars that start off rotating, and so they don't expand very much, and it's kind of just this subchannel isolated binary evolution. But one thing that's interesting about it is that you expect the delay time to be longer than 4 billion years, which is pretty long. And so if I look at that merger rate as a function of redshift, and that's what's shown in blue here, this is what we measured, but now it's normalized to redshift 0, just looking at the shape of it. If the progenitors followed that star formation rate and then experienced these different delays, so in orange here is the star formation rate, and we'd expect the merger rate to look like the star formation rate if delay times were 0 always. Then the merger would happen right as the stars was formed. As we consider progressively longer and longer delay times, so distributions that favor longer and longer delay times, Then we get the peak from redshift 2 to move to much lower redshift, and this shape of the rate as a function of redshift to be much flatter. And this curve corresponds to a delay time distribution. That's 3 billion years. That has a minimum delay of 3 billion years. We can see that is ruled out by the data if the progenitors trace the star formation rate. So we've already ruled out that delay times are always longer than 3 billion years, which is in tension with that one prediction.
Technically, you should draw that picture against luminosity distance because that's the observable, not redshift.
Yes. Yeah. So it's actually interesting. I wrote a paper with a high schooler showing that if you know that the peak should be at redshift 2 and you measure luminosity distances, then you can convert the peak in luminosity distance to the peak in redshift and measure cosmology.
I mean, in reality, there'll be a transfer function that takes you one to the other, and soon we'll know what that transfer function is. Because once you have hundreds, you can just plot the transfer function.
I'm actually a little confused. What, like, if it would, oh, this is a T-min, right?
Yeah,
So
yeah.
it's not. I was wondering why these weren't just shifted versions of each other,
Yeah,
but the distribution is changing as well as T-min.
Yeah, this is changing T-min and fixing the rest of the distribution to be a flattened log distribution.
Okay.
NT, which is
Okay. So it isn't quite end up with this same curve just shifted in time.
Yeah.
Yeah.
You always expect your delay time distributions to have some kind of tail to the largest delay times because those are just systems that started off further apart.
Yeah.
Okay, well, let me skip ahead because there's a related point that I want to make involving globular clusters. And there was a question about this earlier, so then I'm coming back to it. Back to this plot that I showed earlier. So this is the chi-effective cumulative distribution, and before I was pointing out that, okay, less than 3% is fewer than 3% of events have chi-effective below -0.3. But another thing you can get from this plot is the fraction of sources that have chi-effectives smaller than 0, which is also interesting because if you have chi-effective less than 0, then you know that one of your black holes is misaligned from the orbital angular momentum by more than 90 degrees. And generally, we think that's hard to do from isolated stellar evolution. But it's very easy to do in dynamical assembly in dense environments like globular clusters. In fact, we think in globular clusters, half the time you'll have chi-effective less than 0. And so we can look at the fraction of events that have chi-effective less than 0 and turn that into the fraction of sources that are formed in globular clusters, for example, or really an upper limit on the fraction of sources that are formed in globular clusters. Right now, we can say that fraction, so it's less than 50% because we do have this skew to positive chi-effective. So it's probably at most around 60% of sources that are formed in a dynamical assembly channel like in globular clusters.
But these are still first generation. These are 1G plus 1G
These
cases,
are
or anything. Okay.
anything, yeah.
Okay. But your previous stuff suggests they must be 1G plus 1G.
Right.
Okay.
Yeah. Which just means that for like most realistic densities of globular clusters, the 2G ones will actually be pretty rare. So that 20% upper limit is like very comfortable for globular clusters.
You know, I mean, one thing that I'm suspicious about in this argument is that we know that there's planetary systems where the planets are not aligned, that are anti-aligned and at substantial inclinations with respect to the spin of the host star. And we don't think any of those form by dynamical capture.
Yeah, so, right, so this would suggest
The
that.
planets.
That's right.
Yeah, so, yeah, I think I agree with that. I actually haven't thought about the planet context, but I do think that our naive assumptions that, okay, in isolated binary evolution, everything is aligned, that's probably not true. For the sake of this argument, this is an upper limit. The fact that this is an upper limit on the globular cluster rate is still true. It would just be an even stricter upper limit if.
Yeah, and I'm not really objecting to it, but I do think it's very interesting to look at what observational handles we have on for the stars, like for progenitor stars.
Yeah,
Because
yeah.
we know that planetary systems turn out to be arbitrarily complicated.
Another assumption that we always make, which everyone will probably think is justified, but I'm not sure about, is that the black hole spin comes from the stellar core spin.
Right.
Which, okay, for very massive stars, if you have direct collapse, like maybe,
But in the fallback case, that's not obvious.
yeah.
Why is this expressed in terms of globulars specifically?
Okay, yes, because I was working on this project with Giacomo, who has simulations of mergers in globular clusters. So
Okay.
yeah, so
But it's like you don't expect those to happen just in massive but open, unbound
like
clusters.
young star clusters.
Yeah, because it all happens really
it's-
early anyway, right?
Yeah, but they're usually not dense enough for you to really have the same dynamics between black holes. You definitely have dynamics, like stellar dynamics, that's shaping the initial conditions. But after those initial conditions are kind of set, then it's kind of more similar to isolated binary evolution. So you don't really expect to get the same like isotropic spin distribution in those, although those are really difficult to model.
Okay, so you just need to be in a dense enough region that you're going to have an interaction, but the spins are all
Yeah,
random.
that everything will randomize.
Yeah, and so in other situations, you're either not dense enough, or if you're dense enough, you expect things to be correlated. Is that what you mean?
Yeah, in things like triples to open star cluster, those are kind of in the middle of the isolated two dynamics. But it's definitely not dynamical enough for things to, like the spins to totally randomize. Like you still care a lot about initial binaries and things like that. And you still have binaries that stay together for a long time, like as stars, and so align their spins through tides and such.
Okay.
Yeah, but just to wrap up this thing, so one thing we can do is look at again, this is the rate as a function of redshift, but we can look at the total rate, which is what I showed before, but now I flipped it so it's in orange. And then we can look at the dynamics rate, which is in blue. And so this dynamics rate is just taking the total rate and multiplying it by the fraction of systems that's consistent with isotropic spins at these different redshifts. So we get these huge error bars, but the dynamics rate is lower than the total rate. And yeah, so this is really an upper limit on the globular cluster rate. But we can treat it as being equal to the rate of globular clusters for fun, and use that to measure the properties of globular clusters themselves. And so this is showing one example where this blue curve here is again what we've measured in gravitational waves, but now these other curves on this plot are predictions from globular cluster simulations where the virial radius here is varied. And so you can see as you vary the virial radius of your globular cluster, as you have like more dense clusters, your black hole rate is higher. And also evolves slightly faster with redshift than if you have these bigger diffuse clusters. And then maybe I'll just end with this result. So one thing we can do is fit for the globular cluster rate as a function of redshift from that measured gravitational wave dynamics rate. And so that's what's shown here is the rate of star formation in globular clusters as a function of redshift. And basically what we're using is that we have the delay time distribution that we predict from the globular clusters. And so we can turn the merger rate and deconvolve it back with that delay time distribution to get the formation rate and now probe much higher redshifts than we're able to observe the black holes from. And so because this dynamics rate here increases pretty rapidly with redshift, if you believe that's what black holes from globular clusters are doing, you get that the formation rate of globular clusters evolves pretty steeply with redshift and peaks at fairly high redshift. So probably peaks above redshift 3 or so.
But aren't these you're basing these on upper limits of the number of these things that form in globular clusters, right?
Yeah, so this is.
So why aren't these upper limits somehow? Like, why can't none of them form in globular clusters?
Yeah, so this technically is an upper limit, in which case the shape is meaningless, and then you just care about like what the rate is.
Okay.
Which is also interesting because it gives you a constraint on the fraction of clusters that have evaporated, because we have kind of a lower limit on the cluster density based on the clusters that we see in the
Right.
Milky Way,
Yeah.
but we think that a lot of clusters formed and disrupted. So you can use that to get a limit on that, but the shape is pretending that this is the merger rate from globular clusters. So it's a
Okay.
yeah, and then we can also do things like get the globular cluster mass distribution, which in this case is mostly consistent with what people typically assume, which is the Schechter function with the power law slope of -2 up to around 10 to the 6th solar masses. And again, this is, if you treat it as an upper limit, that's basically you get an upper limit on the rate of massive clusters. So you rule out that massive clusters are more common than less massive clusters, because then you overproduce the black hole merger rate.
This is mass distribution at formation.
Yes.
Yeah.
Yeah, so then you get these ones all evaporate, and then you get like the log normal thing for evolved Schechter function. Okay, so this is the summary for that section, but I'll just end with my conclusions. We don't have any more time to ask questions.
That's all right.
But yeah, I'm done.
Okay, let's get we are going to have some time for people to ask questions right now.
So when I was a small child, meaning like 3 years ago, I was told that there really would be this parent-stability mass gap. When you showed that Hager plot, there was no mass gap really in that original 2003 thing. I mean,
There's
it
a
was-
mass gap.
But it was filled in higher metallicities.
Yes.
So it might be.
Time ago.
Um,
Yeah, this here is the mass gap.
So is it that the mass gap, to be observable, it's that the direct black holes up here would be much lower mass than the direct black holes on the far side of the parent stability? Is that what it's? Like, this is in terms of the mass of the star.
Yes.
But of course, the observable is really the mass of the black hole.
Oh, yes. So this is like, if you start off with an initial mass of the star,
Yeah.
140 solar masses,
Yeah.
you lose a bunch of mass, so you end up with a carbon-oxygen core that's like 50 solar masses.
fine, whereas if you get across 260, it all goes into the black hole, or a lot of it does.
Yeah, if you get above 260, then you start to experience the pair instability, but then you
Then
compensate
Add
for
back
that.
it in.
Yeah, so you have additional energy losses due to photodisintegration of your
Fine, yeah.
nuclei, and then the whole thing collapses again.
I see. So there's still this doesn't show the mass gap, but there is in fact a mass gap because this black part is lower mass than
Yeah,
that little corner.
yeah. So right, this at the higher metallicity, the idea is just that you lose so much mass that you're below. You always end up below the mass.
Fine. Good.
It'd be
Yeah.
better if the colors were showing the final mass.
Yeah. We could do a good
Maybe
job
that-
of
Yeah, so if
visualizing
you
the right
look at
thing
the 2023 paper, they have the first two figures are like solar metallicity and zero metallicity, and then it's initial mass versus black hole mass.
And right now, the LIGO statistics don't seem to favor that there is a mass gap, right?
Yeah, so
Or
we
is
do
what's your
have
reading
this.
of the
Because
mass
it's
gap
not really that
situation?
massive, right? Or it's very confusing.
So we have, so if you think the mass gap starts at 40 to 50, so however you.
But in your
say
picture,
45.
that's not where the mass gap started. It was very confusing.
Oh, so
It's
that's
a
in
different
terms of
mass.
the initial mass. So yeah, if you look
That's why
at the
you need to see the
predictions,
final.
yeah, if you look at the predictions for the final mass, then you expect there to be no black holes between around 50 and 130 solar masses. And so we do have black holes there. I think the main thing that is confusing us right now is this P, because this is like the one thing we know that this is the one feature that we have in the black hole mass distribution. At first, we thought, okay, there's a cutoff at 40. Then it turned out, no, it's not a cutoff at 40. It's actually a peak at around 35. And you might get a pileup like this from the pulsation part of pair instability. If you have the pulsations, then you have a lot of black holes that would have collapsed to 60 solar masses. They now lose mass
Yeah.
and form this pileup. But it's just strange because the latest predictions for where the gap should start place it at like 50 to 60 solar masses. And so why would the pileup be at 35 if there's right here? But yeah, so some people will tell you we have seen evidence for pair instability. We have this pileup at 35 solar masses. Other people will tell you, no, that can't be pair instability. And so maybe there is some cliff here, but it's just very, because again, the rates here are already very low. This whole integrated mass distribution here is fewer than 1%.
Yeah. 'Cause you're-
And the reason that we're able to probe it in more detail is because of those selection effects.
Yeah. Which help you. In this case, they help you.
So we have a lot of mergers over here, but still not like
Yeah.
great statistics.
But naively, you would say that imagine you knew for sure that there couldn't be things above 50, then naively you'd say everything above 50 should be dynamically formed.
Yeah.
And then it would have a different chi distribution from the things south of 50.
Right.
So there's a lot more opportunities here for interesting hierarchical studies
Yeah, and I think
that are kind of
combining
hypothesis driven.
combining those two things and saying, okay, where hierarchical mergers take over, I should
Yeah.
have some feature in the mass distribution, and then maybe you can
And also in the
find
chi
it better.
distribution.
So my one wish, well, if I have more than one wish, one of my wishes for 04.
When you give the seminar here, you do get one wish.
Yeah, exactly. There's a genie that we bring out a coffee bag.
Well, okay, I would really like to have an event that's above the gap. Like I
Hell
think
yeah.
if we have 130 solar
That would be
mass
great.
black
That would be
hole.
great. I mean, what do we know about the IMF up there? Are there going to be? There's not much known about the IMF at 160 solar masses, right? So we don't really know if such stars ever form.
Yeah, I mean, these would be stars, like, well, going back to the Hager plot.
Oh
Yeah,
my
these would be
God,
like
yeah.
above 260.
Yeah, I see, yeah. So we have no
At
idea, right?
very
Do we?
subsolar.
So does anybody else have questions?
Yes, right.
If not, let's thank Maya again. And then I will stop the recording. It's Harvick will annoyed with me. Last week, I recorded
Wouldn't
12
expect to
hours,
see anything.
which was
Maybe not, I don't know. What are the most massive stars that ever form? You're the person I would ask.